Okay, I want you to imagine something for a second. Picture heating something up to be hotter than the surface of the sun.
Right.
But you're not using a furnace or, a fusion reactor. You're just using sound waves.
In water, of all places.
Exactly. You're taking sound and turning it into this star-like heat.
That phenomenon, it's called sonoluminescence. And it's genuinely mind-bending.
It sounds like it. So what is it exactly?
In a nutshell, it's the flash of light you get when a bubble in a liquid gets hit by sound waves and then just violently implodes.
And when you say hotter than the sun, you're not exaggerating.
Not at all. The sun's surface is, about 5,800 Kelvin?
Mm-hmm.
We've confirmed temperatures inside these tiny collapsing bubbles get to at least 12,000 Kelvin.
Wow.
Yeah, hot enough to melt steel. And some estimates for the very core of the plasma go up to 20,000 Kelvin.
That's just an insane amount of energy in such a tiny space. I read this was first spotted way back in the 30s.
That's right, 1934, at the University of Cologne. Researchers were working on sonar and just noticed these strange little dots on their photographic film. They didn't really know what they were seeing.
So they couldn't really study it properly back then.
No, not really. The big leap forward came much later, in 1990, with something called stable single-bubble sonoluminescence. SBSL for short.
Okay, and that let them isolate it.
Exactly. It let us trap and study a single stable bubble. And that's when we could measure just how extreme this all is. We're talking about a bubble that's like 1 micrometer across.
Microscopic, then.
Totally. And the flash of light it gives off, it can last for as little as 35 picoseconds.
35 picoseconds. That's an unbelievably short amount of time.
It is.
So you have this tiny bubble, this crazy fast flash of light. But I also heard that what's in the bubble really matters, right?
Oh, absolutely. That's a key piece of the puzzle. If you dissolve a noble gas like argon or xenon into the water, the light gets much, much brighter.
So the gas is like the fuel for the fire.
That's a great way to put it. The gas inside gets superheated and becomes the source of the light.
So how? How are we so sure about these insane temperatures, and what is the actual mechanism that turns sound into light?
That is the million-dollar question. The leading theory is that it's about the inertia of the water. When that bubble collapses, the water around it rushes in so fast.
Okay.
It acts like a piston, slamming down at incredible speed. This creates massive, massive compression, what physicists call adiabatic compression.
And that compression creates the heat.
Extreme heat and pressure, yeah. It rips the electrons off the noble gas atoms, turning the core into a hot plasma. The light we see is mostly something called thermal bremsstrahlung radiation.
Bremsstrahlung. Okay, you're going to have to break that one down for me.
Yeah, it's a bit of a mouthful. It's German for breaking radiation.
Breaking radiation.
Yeah. Essentially, you have these super fast electrons in the plasma. When they get near other atoms and are forced to break or slow down, they release that energy as a flash of light. It's like friction, but at an atomic level.
Yeah. Wow. It's the ultimate example of focusing energy. And what's really wild is that nature actually figured this out ages ago.
It really did.
Yeah.
You just have to look at the pistol shrimp.
The snapping shrimp.
Right, that's the one. It has this specialized claw that it snaps shut so fast it creates one of these collapsing bubbles. The shock wave is actually powerful enough to stun or kill small fish.
And the flash of light is just a byproduct.
It's just a tiny, invisible byproduct. They even have a name for it, shrimpoluminescence. The mantis shrimp can do it too with its powerful little club.
That is incredible. So that brings us to the future then. If a tiny shrimp can do it, surely we can harness it. I've heard whispers of bubble fusion.
Right, and that is the high stakes and, I should say, pretty controversial frontier of this research.
Because fusion needs millions of degrees, not thousands.
Exactly. The challenge is immense.
Yeah.
Can we take this incredible focusing power we see in the bubble and scale it up from 20,000 Kelvin to millions of Kelvin? If we could, you could potentially have thermonuclear fusion in a device that fits on a tabletop.
That would change everything. Tackling challenges that complex, trying to unravel these huge mysteries, it just shows you need the best tools available.
Absolutely.
And this deep dive is actually sponsored by Embersilk. If you're facing complex problems, whether it's AI training, automation, software development, or even just figuring out where AI agents could help your business or your life, you should check them out at embersilk.com.
And, coming back to the practical side, the research is already paying off. Scientists have actually 3D printed devices that mimic the snapping shrimp's claw.
To what end? What can they do with it?
They can use it to reliably generate plasma and those intense shock waves in water on demand.
So we're learning to control it.
We are.
Okay, so here's a final thought for you to chew on. If we can now build these bio-inspired devices to precisely control this ultra-hot, ultra-fast energy, what's next?
Good question.
How soon before we're using these tiny controlled star-in-a-jar moments for things like micromanufacturing or super precise chemical reactions?
It's an inspiring thought. It really shows how we
Yeah.
can observe nature, learn from it, and then engineer solutions that push the boundaries of what's possible. It's a very hopeful area of physics.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.